才能证呀。
行行行，那就 interval 吧，那就这个集合吧，1、2，它的 supreme 是2，对吧？它的 supreme 是2，对吧？你现在证明的是什么？现在我仿照你的思路，我构造一个集合，我构造一个集合，3加 n 分之1，然后那个一加，比如说1加 n 分之1，3加 n 分之1，这是个集合，对吧
？Hello everyone. Sorry. Hello everyone. So we will start today's PDE course. Well, before we start, any question? Any question about well, what we've learned? Any question? Okay, so let me remind you what we've learned in last lecture. Okay, last lecture we basically study the wave equation and well, with initial condition and boundary condition. Okay, and then we find that in general the solution can somehow formally to be written as some kind of sequence. Okay, I think it's sine and x, this kind of sequence, and from 0 to infinity. Okay, formally it can be written in this way. I think we should multiply an cosine nt plus bn sine nt, this kind of thing. Okay, formally. And we also study on a disk the Laplace equation. Okay, with, well, only boundary condition. Okay, and then we also find that the solution, at least formally, it should be able to write it as something like an r to the power n and e to the in theta, and from negative infinity to positive infinity. Okay, and these two forms, they are in some sense the same. Okay, because this kind of coefficient are just some coefficient you suppose to get from the initial condition or the boundary condition. Okay, and then it turns out that the only question for us is whether this kind of formula is available or not, whether this kind of coefficient is uniquely determined or not, and whether this kind of sequence can approximate any kind of function or not. Okay, this seems to be our key problem. So right now, what we're trying to do is we try to study whether a function can be expanded as well, the summation as a series of trigonometry polynomial. You can see that all these kind of terms are just a trigonometry polynomial, which is a polynomial. You plug in cosine and sine. Okay, whatever it is, it's just some polynomial with your x to be cosine theta or sine theta. So we call it a trigonometry polynomial. Okay, for instance, you have cosine n theta here, you have sine n theta here on your sequence, and but we know that we can use some kind of double angle formula or addition formula for the trigonometry function, and eventually it becomes some polynomial of order n of cosine theta. It becomes some polynomial of order n of sine theta. Okay, so which means all these kind of terms are just something like some polynomial of cosine and sine. So we call it approximate, or can be expanded as the polynomial, as the trigonometry polynomial. Okay, so this becomes our question. So we also learned that last time. Well, suppose you have a function, and suppose f theta equals to this summation in the best way we want. Okay, in a way that let's use little an here. In a way that this convergence of this sequence is not only pointwisely but also uniformly. Then in that case, we find that, well, your an must have some particular form, which is 1 over 2 pi from minus pi to pi f theta, well, e to the minus in theta d theta. Okay, your an must of this form if you want this convergence to be something that makes sense. Okay, and then we call this, well, f hat n as the nth coefficient, nth Fourier coefficient of f. Then, well, that means we want to approximate, or we want to expand a function in terms of trigonometry polynomial, and then this trigonometry polynomial must be something that's fixed. Okay, so which means the only problem now is we have to study whether this kind of trigonometry polynomial converge to f theta or not, pointwisely or uniformly, whether that would be possible or not. This becomes our question. Okay, so today we will discuss more about it, and eventually, if we are lucky, if we have enough time, then we will go through this problem. We will go through this elliptic equation or Laplace equation on the unit disk, and then prove that yes, in a lot of cases, well, as long as your boundary condition is not too bad, then this indeed is the solution. Okay, we will prove that very soon. Well, hopefully by the end of this today's lecture. Okay, so again, now our question is whether this kind of sequence, just as a Taylor series, whether the Taylor series converges to your function or not. This would be our question. Before we do that, maybe we should state some kind of preliminary properties as long as we have our Fourier coefficient and Fourier sequence of your f theta. Okay, these are something, well, we will prove it later, and by some properties we will learn later. But at this moment, we can also prove it by some elementary tricks, and this tricks is very nice, but I'm not going to introduce it because it's kind of technical for you. This is so-called the uniqueness of Fourier coefficient series. Okay, which is a proposition says that, well, the Fourier coefficient of a function is actually unique. You cannot add any other stuff to your Fourier coefficient so that your function has this sequence of f hat n and that sequence of f hat n. You cannot have two. You can only have one. So which means, suppose f is an integrable function on a circle. Then with say f hat n equals to 0. If all the Fourier coefficients are equals to 0, then we have f must equals to 0 for any, well, for any theta 0 such that f is continuous on theta 0. Okay, so which means if all the Fourier coefficients are equals to 0, then your f, if f is continuous, then f must equals to 0. Okay, so which means although we don't know that whether f theta is equals to this f hat n e to the I n theta or not, but as long as your f n hat both equals to 0, then f theta, well, as long as your f theta is continuous, they must equals to each other. Okay, so 0, well, all this kind of, well, so that means all this kind of integral equals to 0 for any n implies f theta equals to 0. This is not a very trivial proposition if you write it this way. Okay, you have a lot of things. You have a lot of things where you have a lot of integrals equals to 0. Then you implies f theta equals to 0. Well, f theta, f is continuous at theta. Okay. And as I said, you can check the proof, which is very nice proof on your textbook, on Stan's book, but I'm not going to do it here because later we will have another method which is easier to prove this, and well, it's a little bit too technical for you to understand the proof of this proposition. Okay, but this is an important proposition because we can get some, well, very good corollary from this proposition. For instance, if f is continuous on the whole circle, then, well, and f hat n equals to 0, then f equals to 0, of course. If f is a continuous function and, well, on the circle, and the Fourier coefficient, the Fourier series of f is so-called the absolute convergence, absolutely convergent. Okay, which means if you take the absolute value or the norm as a complex number of each terms and take the sum, then this sequence converge. that is this kind of thing converge, okay? Because the norm of e to the I n theta is just 1. If this kind of sequence converge absolutely, then the Fourier coefficient, well, the Fourier series converge uniformly to fx or f theta. Okay? Or limit as n goes to infinity, as we used this notation before, as nf theta is equals to f theta uniformly. As nf theta is just the partial sum, and from minus n to n, f hat n e to the I n theta. Okay, you take the partial sum and it converge to f theta, and this converge is a uniform convergence. Okay, I'm going to prove this using this uniqueness proposition of Fourier coefficient. Okay. Why is that? Well, first, let's try to look at it and see why this should be true. Okay, you can see that the absolute convergent. The absolute convergent, that simply means you have as a sequence of functions, you have every terms of your functions, of the sequence of your functions is bounded above by some bn, right? As we mentioned before, if you have fnx, you take the sum, and fnx are all bounded by bn, where sum of bn is summable, okay, it converge. Then that means, okay, fnx, this is the idea, fnx will converge uniformly. Okay, this is something we mentioned about uniform convergence, how you can show something is uniform convergent. So this proposition or this criteria is a very useful criteria, and from it we can see that, okay, since every term can be controlled by this fn hat, f hat n, then of course the Fourier coefficient or the Fourier series it converges uniformly. Then that means, okay, the only problem for this corollary, or the only point you have to prove about this corollary, is whether this convergent is converged to f theta or not. Okay, so this would be easy because you know that by this by this one, or this proposition 1 or lemma 1 about the uniform convergence, we know that this f hat n e to the I n theta, and from minus infinity to infinity, it converges to some functions uniformly. Uniformly in theta. Okay, because we say that if every term can be bounded about by some number, and this number, the sequence of number is summable, then we know that this sequence of functions is summable, and this convergent is uniform convergent. So we can get a function by taking the summation of these functions, and then we know that, well, since it converges uniformly, so we know that g n hat is equals to f n hat. By multiplying e to the I minus I n theta and take the integral both sides. And since this convergent is uniformly convergent, so you have only this coefficient will left. Okay, so you get gn hat equals to fn hat, which means, well, we must have g theta equals to f theta. Or that means g minus f, if you treat it as another function, this function's Fourier coefficient, nth Fourier coefficient equals to 0. And this function's nth Fourier coefficient equals to 0, that means this function must identically equals to 0. Okay, so g equals to f, because g I don't know why, but yeah, I don't know why, but it seems that I suddenly be kicked off from our room, and well, anyway, I hope it works now. Does it work now? I think it works now. Okay. So we have g minus f as a function, has all the Fourier coefficient equals to 0. Okay, so that means g minus f has to be identically 0, because g is continuous, because this is uniform convergent, so g is continuous, f is continuous. Okay, so g minus f is continuous, so g minus f must identically equals to 0, because all the Fourier coefficient equals to 0. So which means g equals to f. Okay, so this means if we have the Fourier coefficient, if you can sum them, you can take the sum of them, then this this f can be expanded as a Fourier series, and this expand is actually a uniform expand and uniform convergent. Okay. Any question? And this proposition or this corollary gives us a very nice approximate of what kind of functions you can expand it as a Fourier coefficient, as a Fourier sequence or Fourier series. Okay, which is another corollary. Say that, well, so for what kind of functions the Fourier coefficient, if it converge absolutely, we can build up some kind of criteria to guarantee that this condition is okay for some functions. For instance, if you have a function f is twice continuously differentiable, which means f has a second derivative, and the second derivative of f is is continuous. Okay, then what we have is f hat n is equals to O1 over n squared. This big O notation is something very important. If you learn some course in the algorithm, computational algorithm, or this kind of thing, this notation will appear again and again. And this notation simply means f hat n times n squared, well, you multiply this n squared is something bounded. Doesn't depend on n. Okay? For any n. Or for n is very big. These are the same. Okay? This is the meaning of this big O 1 over n squared. Which means the decay of f hat n is somehow like 1 over n squared as n goes to infinity. Okay? So that means the Fourier series of f converge absolutely and uniformly to f. Okay? Which simply means if you give me a function which is second, at least you can take the second derivative, and after you take the second derivative, this function is still continuous. For instance, if this function is something really nice, is something like some polynomial or something similar to a polynomial, then you can always do the Fourier expansion of this function, and the Fourier coefficient and the Fourier series is actually converged uniformly. Okay, now you don't need to discuss anything like the radius of convergence, right? As long as your function is twice differentiable, which is a very little limited, right? Well, you don't need a lot of limitation of your function. It just needs to be some kind of smooth function. Then your Fourier coefficient or the Fourier series of this function converge uniformly. It is as good as you want. Okay? Is that okay to understand this corollary or theorem? Any question? Any question? This is a very interesting proposition, okay? And it just tells you as long as your function is good enough, you can always do the Fourier expansion. So let's try to prove it and see why this has to be true. Why you get this 1 over n squared. Okay? This is very interesting. Let's see. Suppose f is twice differentiable, okay? Twice continuous differentiable. Then that means this f hat can be written as minus pi to pi f theta e to the in minus in theta d theta. Okay? Now, since we know that f is twice differentiable, okay? So what if we try to use the integration by parts and see this part as some derivative so that we can move the derivative to f and we still get something that makes sense. Okay? Let's try to use the integration by part. And what is the antiderivative of e to the in theta? Well, that's simply e to the minus in theta divided by minus in. Okay? From minus pi to pi. Plus 1 over in, because you have a minus sign, so this is plus, from minus pi to pi, f prime of theta e to the minus in theta d theta. Okay? Let me write it somehow better. Minus pi to pi, f prime of theta e to the minus in theta d theta. Okay? You see, what happens is you have a 1 over n in front of it. Okay? And this term, since f theta is periodic of 2 pi and e to the minus in theta is of period 2 pi, so it disappears. So this equals to 1 over in, well, from minus pi to pi, f prime of theta e to the minus in theta d theta. So how about we do it again? If we do it again, then what happens here is you have 1 over in times f prime of theta e to the minus in theta divided by minus in. From minus pi to pi, again this term disappears. Okay, and then what you have here is additional factor like 1 over in, right? So it's well, 1 over in squared from minus pi to pi f double prime of theta e to the minus in theta d theta. Or minus 1 over n squared minus pi to pi f double prime theta e to the minus in theta d theta. Okay, now you can see. So 2 pi f hat n is equals to 1 over n squared minus pi to pi f double prime theta e to the minus in theta d theta with norm, and it's less or equal than we take f's value inside, then this e to the minus in theta disappear, 1 over n squared minus pi to pi f double prime of theta with f's value d theta. F double prime is continuous, as we mentioned. So this is less or equal than some constant, which is the integral from minus pi to pi of double prime theta with f's value. This is continuous, so it's bounded. So it is bounded. So of course it's well, this integral is bounded above. Okay, over n squared. So f hat n is less or equal than some other constant over n squared. Okay, we have proved that. So that f hat n is bounded above by 1 over n squared, and this sequence is summable. So f hat n is absolutely convergent. So the Fourier series converge uniformly to f. Okay? And essentially, the proof of this proposition essentially use a proposition which is, you can see that this and this, they somehow have some relation, okay? Which is like, if you take the derivative of your function, then you find the Fourier coefficient. What happens is, you can write it in terms of the Fourier coefficient of f, but just by multiplying an in, okay, in front of it. This proposition is very important, okay? This proposition forms the basis of why Fourier coefficient is so useful. Why it's so useful in the sense of, well, differential equation. It's simply because when you try to look at the Fourier coefficient, then the derivative of functions is nothing but some multiplication instead of taking derivative. Okay? So if you try to solve a PDE in the sense of Fourier coefficient, you only need to solve an algebraic equation, because the derivative is not derivative on the Fourier coefficient, it's just a multiplication on the Fourier coefficient. Okay? For instance, if you have some function or some ODEs, say f prime equals to f, okay, this kind of ODEs, then suppose you try to solve it by expand it as Fourier coefficient. Suppose you know that you can expand it. you can expand fx. Okay, suppose your fx is also on the disk, on the circle. Okay, then if you try to expand it both sides of this equation, then you will have f is the summation of f double prime n e to the I n theta. I will n from minus infinity to infinity. F is f hat n e to the I n theta, and from minus infinity to infinity, right? And suppose you want these two guys equals to each other. Then you want these functions equals to each other. You want f hat equals to f hat, right? This is the only thing you want in order to solve this differential equation. You want for any n, this is true. Okay? But that simply means by this kind of proposition, you don't really need to take the derivative and then take the Fourier coefficient, right? You just need to say, okay, if you take one derivative, it's just the times in. If you take two, that means you take minus n squared, f hat n equals to f hat n. So this is something you really want. You don't want anything else, anything other than that. Okay? Then this means, okay, this means what? This means n squared plus 1 times n squared minus 1, I'm sorry, times f hat n must equals to 0 for any n. When does it happen? When does it happen? What kind of function you should have? Or what can we say about this Fourier coefficient, f hat n?
Other than n equals to 1, all the fn, all the coefficient is 0. When n is 1, there exists only coefficient.
Yes, exactly, but not only 1, but also 9, right? We have n from minus infinity to infinity. So that means, well, n is not, when n is not equals to plus or minus 1, then f hat n equals to 0. So that means f must equals to, okay, it only contains two terms, a1 times, well, some constant times e to the I theta plus c2 e to the minus I theta. Okay, so which, if you don't like this kind of complex numbers, you can write it as a cosine theta plus b sine theta.
Professor,
Mm-hmm.
Why can we conclude that say f double prime equals to f, then why does their Fourier
coefficient are equal?
Yeah, why?
Because you can see, well, if f double prime equals to f, right? Then that means, okay, well, these two functions are the same. F double prime minus f equals to 0, right? So that means f double prime minus f must have all the Fourier coefficient equals to 0, right? That simply means, okay, the Fourier coefficient of f double prime is equals to the Fourier coefficient of f, because taking the Fourier coefficient is a linear operation. It's just to multiply something and then take the integral, right? So this just tells you how important it is, or how convenient it is for the Fourier coefficient and, well, and this differential equation. Okay.
I still have a question.
Of course.
Uniqueness of Fourier series, it goes like, if we know that the Fourier coefficients are 0, then we can conclude that f is 0. But here we know that f is 0. Can we conclude that Fourier?
If f is 0, then what is a Fourier coefficient? Then let's say g is 0. Then what is a Fourier coefficient of g?
It's an integration, so it's
an integration, right?
Oh, okay.
d theta e to the minus I n theta d theta. right? So of course, if g equals to 0, this is equals to 0.
So actually, this is an if and only if.
This is if and only if, as long as you know this function is continuous.
Thank you, Professor.
So this is a very good proposition, and which is why this kind of Fourier coefficient or Fourier things is very useful in the sense of differential equation, because it can change a differential equation to an algebraic equation, or it can somehow change an ODE to an algebraic equation and change a PDE to an ODE. Okay. This is a very, very useful tool for you. And at this moment, it's just applicable to the periodic function, not any other function. But later, well, I don't think we have time, but if we do have enough time, then we can say a little bit more about what is a Fourier transform of a function that defines on the whole plane or the whole space. Okay, if we do have time. Then you can see that why it's so useful if you try to solve some real problem, not only for the periodic problem. But basically, they are the same. Okay, basically they are the same. And if you are learning engineer, if you have some engineer background, then you may find that this is so-called Fourier coefficient or Fourier series and the Fourier transform, as I mentioned. And in engineer, we also use something so-called the Laplace transform. And it has a very similar proposition that is also, well, it can, if you take the Laplace transform of a function and you take the Laplace transform of this function's prime, then you can change it to be something like this variables, this is another function, it becomes this variable multiplied some constant times this LF. Okay, so Laplace transform is also somehow useful for a function that is, for functions derivative and solving the ODE. You can try to check it. The Laplace transform is useful for the engineer simply because, well, this Laplace transform is not really well defined, or it's not really well defined for arbitrary functions. You may have some restriction on these functions, but for Fourier transform, it's much better. But unfortunately, Laplace transform is easier for you to calculate in the whole space. But Fourier transform is slightly harder, okay, which is why the Laplace transform is more useful in engineer. Okay, you can check it yourself. And any question?
Professor, still in the example, minus n squared f hat n equals to fn. Why can we conclude that n squared minus 1 f hat is?
Probably I wrote something wrong here, I guess. Yeah, probably it should be this one, right? N squared plus 1. And for any n, then what we need? Then we don't have a solution. I'm sorry. Right, because if you want a periodic function satisfy f double prime equals to f, then what you will need is, I think, f should equals to e to the theta plus e to, a times e to the theta, plus b times e to the minus theta, which is not possible for a periodic function. So maybe I shouldn't write it like this. I should write it like this. Okay, then that is better. Okay, I'm sorry. We should write it like this. Otherwise, you don't have any solution, any periodic solution for this ODE. Well, of course, but this is good, but this is actually not good enough, right? The problem here is, from this kind of Fourier coefficient or Fourier transform method, you can only deal with those kind of things without any coefficient in front. Which I mean, if you have f double prime theta plus f theta equals to 0, then you can use this kind of method. However, if you have some other terms here, like theta times f theta equals to 0, then it will be really complicated in terms of finding this Fourier coefficient of these functions. And there is not really a very trivial expression of this kind of things Fourier transform in terms of the Fourier transform of, or the Fourier series, Fourier coefficient of f. Okay, but here I will introduce another kind of operations which can somehow help you in this kind of sense. Okay, in this kind of case, that is so-called the convolution. Convolution is an operation like multiplication, or like multiplication of two functions or addition of two functions. It's kind of an operation of two functions. Let me write the definition. Okay, so given two functions, two integrable functions, with 2 pi period, say f and g on R or on the circle, because we're on R because we assume it's 2 pi periodic. Then we define f convolved with g. Okay, f star g means f convolved with g. It's a new function. It's a new function on the circle. Well, let's not use this theta. Let's use x, because that makes our notation slightly nicer, which is written as 1 over 2 pi minus pi to pi fy gx minus y dy. Okay. Again, this you can see that it's another function. You take the integral in terms of y, so only x will left. And it is a function of period 2 pi. Okay, it's a periodic function. And if you try to look at it, it somehow looks like, well, what does it look like? It somehow looks like you take g of x, but then you take the translation of g of x, okay? And then you multiply fy of this translation. You try to then take the summary of this kind of thing, which is somehow like you try to take an average of gx with weight fy, with weight f, okay? So it's more or less like an average operation of some functions. And as an example, why we are interested in this kind of convolution operation, as an example, for instance, we can write our Fourier coefficient or the Fourier series, Fourier series of functions as a convolution operation. Okay, why is that? Let's try to write down our partial sum of Fourier coefficient or Fourier series. And from minus n to n, f hat n e to the inx. Okay, this is a Fourier, this is a partial sum of Fourier series. And what's it? What it is? It's we can write by definition, right? F hat n is the integral 1 over 2 pi from minus pi to pi, and f x, let's say fy, because we already use x here, fy e to the minusiny dy e to the inx. Okay, this is not minus, this isiny. And then we can put this part inside, right? So it's a summation of n from minus n to n 1 over 2 pi and minus pi to pi e to the in x minus y fy dy. Okay, and this is only a finite sum, so that's switch this sum and this integral. So then it becomes 1 over 2 pi minus pi to pi. The summation, well, you only have n here, right? And from minus n to n e to the I n x minus y fy dy. Okay? Okay. Now that means if you treat this as a function, then this Snfx is nothing but f convolved with this function, where this function is equals to, this is x minus y, is its variable, and from minus n to n e to the I nx. Okay? Moreover, this is what? This is nothing but a geometric series, right? This is nothing but e to the ix to the power n. And you can use the formula to compute it explicitly. It's e to the minus n minus 1, e to the minus inx, capital Nx, and minus e to the minus e to the 0 divided by e to the ix minus 1, and plus a negative part. Okay, because this is a geometric series, you can simplify it, and eventually you find that amazingly it equals to this. Okay, and sometimes we give it a name. Dn is so-called the nth Dirichlet kernel. Well, we call it a kernel just because it's a function and we always use this function to do the convolution operation. Okay, so for those kind of function, we always do it by this convolution. We call it a kernel. Okay, so this is so-called a Dirichlet kernel. And that's good. That means at least what we need to find is not serious. It's not a lot of functions. We sum them up. Eventually, if we want to show some convergent, we just need to show, okay, a convolution convergent, right? The convolution of this function, whatever it is, it's just some functions with parameter n and convolve with f. And then we want to see whether this guy tends to fx or not, as n, capital N goes to infinity, right? This is just an example, and well, now let me write down some very important proposition of the convolution operation, so that you will see why this convolution is a very nice operation in analysis. Okay. Well, let's say f, g, and h are both 2 pi periodic integrable function. Well, it just needs to be integrable, okay? Because on the definition, we don't need anything else. We just need the integrability of this f and g. Then we have first, f convolved with g plus h is equals to f convolved with g plus f convolved with h. Okay? It's just like you can distribute these functions to two functions. Okay? Just like multiplication. And the second, if you have some function, well, if you have some constant times f, evaluate, well, convolved with g is equal to c f convolved with g, or is f convolved with cg. Okay, for any c in R. No, you can imagine, of course, this is true because after all, it's just a convolution of two functions. It's just some integral of two functions. And thirdly, f convolved with g is equals to g convolved with f. Okay, so which means this kind of convolution is actually the same as you switch this f and g and say, okay, it's gy f x minus y dy. Okay, it doesn't change. Well, why it doesn't change? This is a homework exercise for this one, because I think this is a good exercise for you, and it's just a very simple application of change of variables and f and g of period 2 pi. Okay. And 4. If you have f convolved with g convolved with h, is the same as f convolved with g convolved with h. So this operation is associative. Okay, it's associative, commutative, and distributive operation. Okay, and 5. This is very interesting. F convolved with g. You only have f and g are integrable. Okay, so which means your f and g could be very rough, because we know that f and g to be integrable doesn't mean f and g to be continuous. Okay. However, if you take this kind of averaging operation or the convolution operation, you got a better function. It's continuous, which somehow makes sense, because if you try to take an average of a function, then for a rough function, you probably will get something better. You get something not so rough. Okay, so here the convolution of two functions has better smoothness of these two functions. Okay, and well, I'm not going to prove it here, but well, similarly, what you can show is if f or g is differentiable, continuously differentiable, one of them is differentiable, then so is f convolved with g. Okay, for instance, f is continuous differentiable, f is differentiable, then if you take the derivative of f convolved with g is actually equals to f, you take derivative convolved with g. Okay, so which means at least the convolution will give you the best, well, the better regularity of f and g. Okay, if one of them is differentiable and you convolve with another guy, then it's differentiable. If one of them is twice differentiable, then you convolve with another guy, it is twice differentiable. It becomes a twice differentiable function. Okay, and moreover, you can actually change the derivative to one of them. You can change it to one of them, either one of them, as long as it makes sense. Okay, this is a very useful population. And lastly, this is why it's important in terms of the Fourier analysis. F convolved with G. If you try to find the Fourier coefficient of it, what you have is the multiplication of the Fourier coefficient of F and G. Okay, which says that if you have a multiplication on the Fourier side, on the Fourier coefficient, then on this real function side, what you have must be the convolution operation. And the good thing here is, well, you can actually do the conversely. You can actually do it conversely, which means if you have the multiplication of two functions, then you take the this Fourier coefficient of the multiplication of two functions. Here, what you should have is a convolution. It's a convolution of the Fourier coefficient. But of course, what is a convolution of Fourier coefficient? I didn't tell you, but you can imagine what it is. Just change the integral to the summation. Then what you get is a convolution of two sequences. Okay. Here, since we are not going to talk more about it here, probably I will just leave it as an exercise and think about it. Okay, how you can write this term in terms of the Fourier coefficient of f and g. This is an exercise for you. Okay. Let me prove this kind of proposition of Fourier coefficient. Let's prove it. Before we prove it, any question? Understanding of this proposition? Any question? Okay, so let's prove it. Well, first of all, let's say that if this proof of this is quite standard and analysis way to prove this proposition, which is somehow like approximation method. Let's say if f and g are both continuous. Suppose we are able to prove these propositions for those continuous functions. The idea here is, suppose we are able to prove this proposition for continuous function. Then for general integrable function, what we need is, if we want to prove this proposition, we just need to do an approximation of this integrable function by using continuous function. Okay, so let's first try to prove this proposition for continuous function. Then we will see how we can do the approximation. Okay, now suppose let's first say that suppose f and g, and h are both continuous function. I'm not going to prove 1, I'm not going to prove 2, I'm not going to prove 3 because 3 is your homework exercise and 1 and 2 are quite simple. Okay, so let's just prove that, and also 4 is also very simple, so I'm not going to prove them. You can just do that by do some change of variables. I'm just going to prove this 5 and 6. Okay. So, let's try to prove 5 and 6. So let's, for instance, if f and g are both continuous, let's try to do 6 first. Okay, f convolved with g, you take the Fourier coefficient of, at the nth Fourier coefficient. Okay, then it's 1 over 2 pi minus pi to pi f convolved with g at x e to the minus inx dx. Okay, then this becomes pretty simple. 1 over 2 pi minus pi to pi. F convolved with g is 1 over 2 pi integral of fy gx minus y dy e to the minus inx dx. Okay, I just write it, expand it by definition. Then what you can see is you have an e to the minus inx here, but you have y and x minus y here inside. So, which makes us try to write it, this is minus pi to pi, like this. We pair with fy with e to the minusiny. And pair this gx minus y with e to the minus in x minus y. You have dy dx. Okay, so we did nothing, just trying to put this term inside and split it into two parts. One pair with this fy, one pair with gx minus 1. Now, since your g and f are both continuous, so the inner part, the integrand, is continuous, right? So which means we can switch the order of the integration. I hope you know this. You can switch dx and dy. Okay? With well, this term, you take the integral of y. And the rest only depends on, well, integral of x. The rest only depends on y. Dx multiplied by fy dy. Okay? This is because of continuity. Otherwise, you cannot really do it like this. You may not be able to do it like this, okay? And then you can see that then this inner part is a translation, right? And this is a translation so that you can do a change of variable. But be careful, if you do a change of variable, then this will be minus pi plus y and the pi plus y, okay? But as I said, this is an exercise to say that if you take from minus pi plus y to pi plus y, it's still, you take the integral of g times e to the minus inx in a period of this function. So this doesn't change the value of integration. So which means it still equals to minus pi to pi g of x e to the minus inx dx times fy dy. Okay, by change of variable and the use of periodicity of g times e to the minus in. Okay, then what's this? Well, you can see that is 1 over, well, if you pair with it with 1 over 2 pi, it is f, well, this is g hat n fy, I forgot e to the minus iny dy and e to the minus iny dy, e to the minus iny dy. Okay, so this is g hat n because it's just a constant, 1 over 2 pi minus pi to pi fy e to the minus iny dy, so it's g hat n f hat n. Okay, so you get it. Any question?
Why the range of integration doesn't change?
Well, as I said, if you change the integration here, minus pi plus y and pi plus y, g of x e to the minus inx dx. If you change it like this is a function of period 2 pi, right? And you take the integral over the period, well, over integral of length 2 pi. Then it doesn't change this integration. The rigorous proof is your homework. The rigorous proof of this is your homework.
Okay, thank you.
But you can imagine if you have a function, of period 2 pi, something like sine function, then if you take the integral from 0 to 2 pi, it doesn't change if you take the integral from some point here to some point here plus 2 pi. Okay, the integration doesn't change. You can shift it as long as you have the length of the integral, the length of the interval to be 2 pi. Okay, you can change it, you can shift it geometrically. But of course, you will need to prove it. This is 6. Seems to be very easy, right? Then let's prove 5. F convolved with G is continuous. Say if F and G are both continuous, then what we need to do is, okay, if x1 minus x2 is small, then we must have, F convolved with G evaluated at x1 minus F convolved with G evaluated at x2 is also very small. Okay? So given epsilon, well, we want to find that delta is greater than 0 such that F convolved with G evaluated at x1 minus F convolved with G evaluated at x2 is less than epsilon whenever x1 minus x2 is less than delta. By the way, well, be careful here. This is slightly different from the definition of continuity that you learned in calculus 1. Because in calculus 1, you discuss about the point, the function, whether a function is continuous or not at one point, right? So for different points, you may have different delta, depends on the different delta dependent of epsilon. But this kind of continuity, which is a continuity as long as you have 2 points is with distance very small, you have the value of the functions is very small. This kind of continuity is so-called uniform continuity. Uniform continuity over an interval. Okay, uniform simply means, well, whatever you want, as long as you have 2 points, then you want this value of these functions at least 2 points are very small. So it's uniformly in the sense of the point you choose. So which is why we call it a uniform continuity. Okay, have you heard about this term, uniform continuity? Who have heard about this? You can raise your hand. Okay, maybe I should say a little bit more about the uniform continuity. Okay, this is a side mark. In the usual way, if we try to say f, a function, is continuous at a point, well, f is continuous at x0, that means for any epsilon you give me, there exists a delta which depends on epsilon, and it also depends on x0, okay? Such that if x minus x0, if your point x is close enough to x0, we have fx minus fx0 is less than epsilon. Your value of your function is close enough to the value at x0. This is the meaning of continuous at x0. Then, what is a uniform continuity? Well, we always discuss a uniform continuity over an interval, okay? Or over some set of points. Okay, say S. S is a subset of R, let's say. Okay, and what's the meaning of uniform continuity over S? That means for any epsilon greater than 0, there exists a delta that doesn't depend on the point you choose, but it only depends on epsilon, okay? Such that if you have x minus, if for any point you choose from S, for any point x1 in S, for any point, arbitrary point, then if x minus x1 is less than delta, implies fx minus fx1 is less than epsilon. So which means this delta you choose, it doesn't depend on the point you choose. It's uniformly among this whole set S. Okay? This is so-called the uniform continuity. And there is a very important proposition. There is a very important proposition says that if f is continuous on a closed interval, say AB, then f is uniformly continuous. So continuous on a closed interval, closed bounded interval means uniformly continuous. Okay, this is a very basic and very important proposition in mathematical analysis. I believe you can find it from your real analysis book. Okay, I believe you can find it. And you can try to check the proof of it by yourself. Okay, the essential part is just like the maximum, the Newton's principle, or I forgot Fermat's principle. That is the compactness of this closed interval. Okay. So here we want to show that f convolved with g is continuous. It's continuous over the closed interval from minus pi to pi, right? Because it's periodic. It's 2 pi periodic. So the only thing we want to show, well, by the way, so this uniform continuous over an interval is, of course, well, stronger than the continuous over the closed interval, right? Or continuous over the set. So it's a stronger restriction. Uniform continuous means it's continuous. Of course, it must be continuous at each point of your set S. Okay. So here, if you want to show that f convolved with g is continuous over minus pi to pi, well, if we can show that f convolved with g is uniformly continuous, then we are done, right? So let's try to show this. It's uniformly continuous. It's not necessary, but since we just learned that, let's try to make application of the uniform continuous. That is what we said. For any epsilon greater than 0, we want to find delta greater than 0 such that, well, x1 minus x2 is less than delta, implies f convolved with g at x1 minus f convolved with g at x2 is less than epsilon. Okay, let's try to show this. How can we show this? Well, let's try to expand it. Let's try to write it and see whether we can find some data based on epsilon or not. So f convolved with g evaluated at x1 minus f convolved with g evaluated at x2 is equals to what? It's 1 over 2 pi minus pi to pi g, well, f of y, g of x1 minus y, subtract g of x2 minus y, dy. Right? We just combine these two terms and then check this difference. Okay, that's good because G is continuous. We assume that f and g are both continuous, implies G is uniformly continuous over the minus pi to pi, right? So, well, there exists a delta greater than 0 such that g of x1 minus y minus g of x2 minus y is less or equal than, well, let's say epsilon whenever x1 minus y minus x2 minus y, which equals to x1 minus x2 is less than delta. Okay? So f convolved with gx1 minus f convolved with gx2 is less or equal than, we take the absolute value inside, well, it's epsilon times 1 over 2 pi minus pi to pi fy dy. F is bounded above. So you see, well, it's less or equal than epsilon times b, where b is a bound. Fy is bounded above by b. Okay? So we are done because this b is just a constant. So we can choose epsilon prime equals to, well, so we basically get, if we choose, I'll say delta equals to this, choose delta such that g of x1 minus y minus g of x2 minus y is less than not only epsilon, but epsilon over b. Okay, whenever delta prime x1 minus y minus x2 minus y is less than delta prime, then what we have is f convolved with gx1 minus f convolved with gx2 is less or equal than epsilon whenever, well, x1 minus x2 is less than delta prime. So delta prime is what we want. So we prove that. It's uniformly continuous, and of course it's continuous. Okay? So what if f and g are just integrable? What happens? How we can solve the problems with only the integrability without this continuity? This is something I'm going to tell you in a minute, but before that, let's have a short break, like 10 minutes break. We'll resume at 32. Okay? Okay, let's start. Now we prove that if f and g are both continuous, then the proposition 5 and 6, and also this first 4 propositions are true about this convolution. Now, what if we only have f and g are integrable, not really continuous? How we can conclude that, for instance, f convolved with g is continuous? This is something very interesting, which is something very useful when you deal with some analysis problem in the future, which we will use a lemma, which is a lemma about approximation. Okay? Suppose f is integrable and bounded by, say, by a number b, okay, on the circle. Then there exists a family of functions, Fn, n from 1 to infinity, okay? of continuous functions. Such that, well, they are uniformly bounded above. Well, let's say this x and k. They are uniformly bounded above. And if you take the difference between these two functions and take the integral, it tends to 0 as k goes to infinity. Okay, but this this is actually a proposition that says that you can always approximate a function, an integrable function, by continuous function. The real theorem actually is stronger than this. You can use a Weierstrass theorem. Stone-Weierstrass theorem says that if you have some functions on a closed interval, then you can always use a polynomial sequence to approximate it uniformly. Or, as later we will see, if you have some function that is integrable, then you can always use, as we mentioned before, you can always use the polynomial, trigonometry polynomial to approximate it uniformly, actually. But of course, it can always be like fk minus f. You take the integral, tends to 0. Okay? We will see that, and we will show that in the future. But you can also check it, I think, on appendix of Stan's book, or you can also check the Stone-Weierstrass theorem. So this just says that you can use some polynomial or use some trigonometry polynomial to approximate an integrable function. Okay, I'm not going to prove it. Then, and also, don't forget, the polynomial or this trigonometry polynomial always be uniformly bounded. Okay, then after this, we can show all the propositions, from continuous function to integrable function. Okay. For instance, let's use this kind of method to show. Let's use this kind of method to show. For instance, f. This is 5. F convolved with g is continuous. Okay, but f and g are both integrable, not continuous. How we can show this? Well, we can show it like this. Again, you want to show something about f convolved with g. We only know something continuous happen, right? So let's say, okay, since your f and g are both 2π periodic and integrable functions, so they are bounded. Well, this is Riemann integrability, so integrable means bounded above. Okay, then we can, by this lemma, to choose a sequence, a family of functions which are continuous to approximate f and approximate g. Okay, and let's see what happens if we choose this kind of sequence to approximate it. And let's try to evaluate the difference between these two guys. How we can do that? It's just like when you try to show something about multiplication. That's trying to insert one term and subtract that term, okay? That's trying to insert fk convolved with g and plus fk convolved with g. Then what happens here is it will becomes f minus fk convolved with g plus fk convolved with g minus gk. Okay. Then now what we need to show is somehow like both of these two will converge to 0 uniformly. Then we can show that this sequence of functions converge to f convolved with g uniformly. Then since this function, all these functions are continuous, so f convolved with g is also continuous. Okay? So let's try to show this will tend to 0 as k goes to infinity. What is this? Well, this is nothing but an integral minus pi to pi fx minus y minus fk x minus y times g of y dy. Okay. So of course, if you take f's value here, then it's less or equal than 1 over 2 pi, the maximum of g, times the integral from minus pi to pi fx minus fkx, well, y dy. Okay. Then, what's this? This is something bounded about by some constant times the integral from minus pi to pi fy minus fky dy. It tends to 0 uniformly. Okay? So this term will tend to 0 uniformly. No matter what x you give me, it will tend to 0 uniformly. So does the other term. Fk convolved with g minus gk is equals to, well, 1 over 2 pi minus pi to pi. That would be fk of y or x minus y, it doesn't matter, g of x minus y minus gk of x minus y dy. And it's less or equal than 1 over 2 pi, the supremum of fk, or the maximum value of fk, times the integral of this dy. And it tends to 0 just as before, uniformly. Okay, so it doesn't depend on the x you gave me. So this means f convolved with g can be approximating by fk convolved with gk uniformly. Okay, and similarly for this 6, you can prove it by yourself. So we are done. As long as we have this kind of properties of continuous function, we have the corresponding properties of the integrable function. Okay? Any question? Any question? Okay. Now we have all the properties about the convolution. Okay, but the convolution it doesn't really help us in order to deal with this kind of convergent problem. We still need to study what kind of Dn it is. And then based on the properties of convolution operation, maybe we can get something about the convergence. This is so-called the good kernel. Okay, we will study so-called the good kernel, or somebody call it the approximation of identity in order to study the convergent property of the sequence, okay, of the Fourier sequence or the Fourier series. So remember, what we want to study is this kind of kernel, and whether this kernel has some good property or not. Okay, so good kernel. What would be a good kernel? A family of kernels. Remember what is kernels? Is some functions we use it to do the convolution. Okay, knx from 1 to infinity on the circle, which means it's a periodic functions. All the functions are periodic functions on the circle is said to be a family of good kernel. Good kernels if it satisfies the following 3 propositions. 1, for all n greater or equal than 1, the integral of this kernel must be normalized, which means the integral of this kernel must be equals to 1. You'll see why. Okay, I'll explain it why we want all the kernel has integral equals to 1. And second, there exists some n which is greater than 0, such that if you want to take the integral of this kn, but with absolute value, okay? If you take the integral of the kn, well, it equals to 1, then that's good. But if you take the absolute value of this kn, it's bounded above, okay? So which means your kn shouldn't be oscillate a lot. It cannot oscillate a lot. Okay. And third, for any delta is greater than 0, then if you take the integral, if you take the integral from minus pi to pi, but with x is not very close to 0. Okay? If you take this kind of integral with x not very close to 0, it tends to 0 as n goes to infinity. Okay? So what's the intuition? What do we want to model, or what do we want to define? What kind of good kernels are in our mind? Here is an explanation about what kind of things we are going to call it a good thing. Okay, what is really a good kernel? A good kernel is what? A good kernel, based on this two, is just some very smooth, maybe something very smooth functions. But what does the third mean? What does this third property means? For instance, in general, let's say Kn is greater than 0, because most of the good kernel we are dealing with are always positive. Okay, so that it makes it a little bit easier for us to understand. And what does this mean? This means your kernel could have a lot of perturbation, but it must have some concentration around 0. And it must be more and more concentrate at the origin. More and more as n goes to infinity. And as n goes to infinity, then it basically like everything, all the mass of the kernel concentrate on the origin. Which means if you try to keep some window around the origin, then the rest of this kernel, the rest of these functions will be smaller and smaller and smaller. Okay, so which means it will more and more and more concentrated on the origin. This is what we want. This is a kernel that we want. Okay, and in the sense of convolution, say F convolved with this kind of kernel. What does it look like? It looks like minus pi to pi f x minus y kn of y dy, right? Remember, we say that this kind of operation is something like you try to do a shift of f and then take it as a weight and then do the average. If we have this kind of kernel, what does that mean? That means you will have a very heavily weight on the origin on y equals to 0, right? You have a very heavily weight on y equals to 0, and that means, okay, it somehow will tends to fx. This kind of thing will somehow concentrate on fx, and all the rest are not important. All the other translation are not so important. Just the one y equals to 0 are the most important part, which is why we call it a good kernel, because this kernel, as n goes to infinity, will somehow concentrate on fx. Okay? And this kind of kernel, in some sense, well, you haven't learned what is functional analysis, but in some sense, it tends to another very ugly or very fancy functions. Well, I use a caution because it's not really a function. It's so-called a generalized function, so-called Dirac delta. Dirac delta function, which is not really a function because delta x is equals to infinity when x is equals to 0, is equals to 0 when x is not equals to 0. Okay, you can imagine this, this kind of family of good kernel is you try to approximate this kind of function. And the good thing is, if you have a good definition of this kind of Dirac delta function, then you will see that this Dirac delta function will act as an identity over this, convolution operation. But of course, this delta x is not a real function. It's not really a function. Okay, this is so-called a generalized function. This is an intuition about good kernel. In some literature, good kernel is also be called as approximation of identity. Because identity, the real identity of the convolution operation is not a real function. So we have to use a family of functions to approximate it. Okay? So as our intuition tells us, then if you have something like a good kernel, then what we do have is, it can really approximate the identity. If we have a family of good kernel, and f is integrable function on a circle, then what we have is the limit as n goes to infinity, f convolved with kn is equals to fx, whenever f is continuous at x. Okay, and if f is continuous over, everywhere, then this limit converge uniformly. This is a uniform convergence. Okay, Any question about this, this theorems and good kernel before we move on, before I prove these theorems? Any question? Any question? Okay, let's prove it. Well, the proof is actually pretty straightforward in some sense. Okay, let's say we want to show that this function approximates to that function. So let's say we have an epsilon greater than 0, f is continuous at x. We choose delta such that y is less than delta implies fx minus y minus fy is less than epsilon. Okay, then the proof is also very analysis. You can see this kind of proof in the future again and again if you're studying analysis. Okay, then let's see what is f combined with kn minus fx. Well, it's equals to 1 over 2 pi minus pi to pi kn of y fx minus y minus fx. You see here, what did we do here? We just move this fx. We move, well, from outside. Maybe I should write it step by step. Just make sure that you could follow it. This f, well, is 1 over 2 pi from minus pi to pi, f x minus y, kn of y dy minus fx. Then, since the integral of kn equals to 1, we use a normalization condition of this kernel. So you can write this fx as the integral of fx times kny dy, right? Because the integral of kny is equals to 1. So you can combine this term and write it as 1 over 2 pi minus pi to pi fx minus y minus fx. Kn of y dy. Okay? Because fx times kny, you take the integral, is equals to fx. So this means, okay, if y is small, then fx minus fx minus y is small. Otherwise, if y is not small, then how can we deal with it? If y is not very small, then these two may have a very big difference. However, we can see that the integration of k and y could be very small, right? Either this term is very small or this term is very small. So which means in order to show this whole thing is very small, we only need to split it into two parts and discuss them part by part. Okay, so this integration is equals to 1 over 2 pi, and you have, if y is greater than delta, less than pi, you have fx minus y minus fx. This term may not be very small, right? But kny dy is very small as n goes to infinity. Okay? Plus y is less than delta, fx minus y minus fx times kny dy. This term, fx minus y minus fx, is very small, and kn is somehow bounded above. Okay, so which means it's also very small. So this is less or equal than 1 over 2 pi, as we mentioned, delta less than y less than pi, and fx minus y minus fx times kn of y, you accept value, dy, plus y is less than delta fx minus y minus fx times kn of y dy. You know that this is less or equal than, well, some epsilon times 1 over 2 pi, the integral from, I'm sorry, this term, well, maybe I should write it in some other way. So if n is bigger than some capital N0, which is something very big, then we know that this term is less or equal than, well, the bound of fx times 2 divided by 2 pi times something very small. This term will go to 0, right? So we can choose something very, very small so that it's less than this very small stuff. Plus, this term is less or equal than epsilon times 2 pi, y is less than delta, kn of y, but kn of y, you take the integral over this, well, near the 0, so it's still bounded about because it's less or equal than, well, b over pi times this term could be very small, let's say epsilon, plus epsilon times 1 over 2 pi, you take the integral from minus pi to pi. Of course, you take a larger interval, and this is something positive, so it's less or equal than this. Okay, so it's less or equal than b over pi plus this is m over 2 pi, which is nothing but a constant times epsilon. As long as you take n big enough, you choose delta big enough, so you can choose epsilon so that it's well, it's less or equal than epsilon 0 or whatever you want. So that means by epsilon delta language, that simply means f convolved with kn of x. If you take the limit as n goes to infinity, it equals to fx. Okay, and this convergent is uniformly convergent because if fx is continuous everywhere, then it's uniform continuous everywhere. It's uniformly continuous over the interval. So that means this y, this delta is uniformly, it's independent of x, so this limit is uniformly convergent. Okay, so we are done. Which means if your kernel is a good kernel, it's a family of good kernel, then it is approximation of identity. It can, after you take the convolution, it can approximate to the function itself. Any question? Any question? Okay, then that's perfect, because that means we only, if we want to check whether this guy tends to f or not, we only need to check whether this dn is a good kernel or not, right? If it is a good kernel, then we are done. Okay. And what is dn? Well, dn is not very bad. It's sine n plus 1/2 x over sine 1/2 x. Is this a good kernel? Well, not so sure, right? So let's check these conditions. Let's check them one by one. First, if you take the integral of this from minus pi to pi, dn of x dx My claim is it must equals to 1. Why is that? Can you see that? Why is that? Why this integral of this dn is equals to 1? Any idea? Any idea? If you take the integral of this guy, what do you get? If you take the integral of this guy, what do you get? E to the minus inx, if you take the integral.
Other than n is 0, everything is 0.
Exactly, right? Every other thing just have pair of 2 pi, and if you take the integral, it will still be a pair of 2 pi, and it's just a 0. But 1, if you take the integral, you will get 1, right? So yes, of course, you take the integral, it equals to 1. And if you check the third one, well, 1 over 2 pi, x is greater than delta less than pi, dn of x, it indeed tends to 0. Because if x is greater than delta, then the denominator is greater or equal than something depends on delta, right? Sine 1/2 delta, and it's a fixed constant. And so this kind of integration is less or equal than sine n plus 1/2 x, something like this. Okay, and then you can try to take the integral and see whether it's equals to it tends to 0 or not. Well, I didn't really check that, but you can check this whether this is true or not. However, this might be true for the third part. However, in your homework, there will be a problem ask you to show if you take the integral from minus pi to pi dnx, it's actually greater or equal than log n. Okay? Which means that this dnx is not really bounded above if you take that value and take the integral. Which means that this kernel, it somehow looks like this kind of thing. It has a lot of oscillation. Although this oscillation could be smaller and smaller and smaller, but if you take that value, then this kind of oscillation, if you take the sum, it is of order very big. It is of order log n. Okay? So the oscillation is too much, which means dn of x is not a family of good kernel, unfortunately. And you can actually show that if you have f convolved with dn for some f, even f is continuous, you don't have any convergent. It will diverge everywhere. This is an example that you can check Stan's book on chapter 3. Okay? And well, so unfortunately, there's no free lunch for us. We still need to struggle a little bit because this kind of thing will not really convergent. If you f is not really twice differentiable, right? This will not convergent if you do not have f to be very smooth, unfortunately. But although it will not convergent, something else can still satisfy what we want, or at least tell us something about this trigonometry polynomial. Okay, this is something so-called the Cheslow summation and Abel summation. the Cheslow and Abel summability of a sequence. Okay. Here, after you know this, you can solve a lot of very interesting problems in mathematical analysis. First, what is the Cheslow summation? Well, suppose you have a sequence and until Cn, which is sum k from 0 to infinity ck. You always wonder whether it converges or not, right? And sometimes it converges, sometimes it does not. For instance, if you have 1 plus minus 1 plus 1 plus minus 1 and so on, we know that from mathematical analysis or from calculus 1, it will not converge, right? It is a summation of 1 minus 1 to the power k from 0 to infinity. And it's actually equals to 1 plus minus 1 to the power n divided by 2 as n goes to infinity, right? And you see that this does not have a limit. Well, however, this is the way we try to take a sum and it does not have a limit. However, if we try to switch the way we take a sum, then what happens is, amazingly, you will find this kind of, well, I don't think we have divide by 2. I'm sorry. The summation is 1 plus minus 1 to the power n, I believe. Yeah. Yeah, I think I'm right. This one. So for this one, you can see that it's well, as if you take some capital N, then either you get 1 here, or you get 0. 1 and 0, 1 and 0, 1 and 0. It will switch and appears again. So somehow we may try to say that the summation of this should somehow be 1/2, right? In some sense, it may be 1/2. But in what sense it should be equals to 1/2? This is how you take this Cheslow summation. Let's call this Sn. For instance, you have Ck to be k from 0 to n Ck. Okay, this is a partial sum of your summation of your sequence, a partial sum of a sequence. Then what we can do is we can define the average of this partial sum. S0 plus S1 until Sn minus 1 divided by n. This is so-called the nth Cheslow mean of Sk, or the nth Cheslow sum of Ck. So which means you try to take an average. You try to take an average for the partial sum. Then what happens is, well, for instance, what happens here? What happens to this sequence? What happens to this sequence? This will diverge, so it doesn't make sense. But what happens to this Cheslow means of Sn, or the Cheslow sum of this sequence? Well, the Cheslow sum of this sequence would be, okay, you have n on the bottom, you have 1 plus 0 plus 1 plus 0, because the partial sum is either 1 or 0, right? So you can imagine that half of this Sn is 1. Half of them is 0. About half of them is 1, about half of them is 0. So you can see that sigma n should tend to a half. Okay, I didn't prove it rigorously, but you can try to prove it by yourself. Just some expression, okay? So you can see that although this sequence is not summable, this sequence diverges, but the Cheslow means of this sequence is actually converge. There is a proposition say that, well, if you have Sn tends to A, then we must have sigma n tends to A as n goes to infinity. However, sigma n tends to A doesn't mean Sn tends to A. So which means Chesalo's summability is weaker than summability. Okay. Of a sequence. Okay. This is again. This would be a very interesting proposition, and I'm thinking whether I should assign it as a homework or not. You can try to do it if I don't assign it, but if I assign it, you have to do it in your homework. Okay. And there is a so-called Fayet's theorem. As long as you know the Chesalo means of some summation, which is the Chesalo means of Fourier series converge to fx at x continuous. And if f is continuous everywhere, then this convergent is uniform convergent. Okay? Why is that? Well, again, in order to see this, it's very easy. We only need to try to write it as a convolution and find the kernel, and then say it is a good kernel. Let's see. So what is sigma n of fx? Sigma n of fx is a partial sum of fx, and you take the average. You take this average, okay? And it's actually equals to f convolved with another kernel, where this another kernel is d0, because S0f is a convolution of f and d0. And this is convolution of f and dn minus 1. So fn is nothing but the average of all this Dirichlet kernel. Okay? And if you try to write it as this will e to the inx, if you try to write it, because dn is what? dn is a summation of this, so it's equals to e to the inx minus e to the minus inx plus something divided by something, right? So which means what kind of thing you have here is nothing but another geometric series. So you can simplify it, and then after you simplify it, you find that it's actually 1 over n, it's still 1 over n, but with sine square nx over 2 divided by sine square x over 2. This kernel is so-called the Fourier kernel. Okay? And in order to show this, we have a very easy theorem. The Fourier kernel is a family of good kernels. Although the Dirichlet kernel is not a family of good kernels, but if you take the average of them, it becomes a good kernel. Okay? The proof is quite simple. Just a few lines. If you want to check one, of course it is true because all the integral of dn is just a 1. So you have capital N's 1 and divide by capital N. So the integral of fn is 1. Okay? From this definition. Second, well, you see that the Fourier kernel is a positive kernel. So of course, this integral is equals to this integral, which equals to 2 pi. It's bounded above, right? Okay, last thing we need to show is the concentration on the origin, right? Why it concentrate on the origin? Well, if x is away from 0, okay, let's see. The integration will only have something singular at the origin because you have something like 0 near the origin, right? So that means there exists some constant delta, we'll see delta, such that sine square x over 2 is greater or equal than, say, delta. Actually, so delta is equals to sine square delta over 2, okay? So which means this integral along this region fn of x dx is less or equal than, well, 1 over c delta times the integral of well, from minus pi to pi 1 over n sine square nx over 2 dx. Whoa, that's nice. Because what is the inner part? It's just 1 over n times something bounded by 1. Sine square is always less or equal than 1. Right? So it's 1 over c delta times 1 over n times 2 pi, which tends to 0 as n goes to infinity. So this means the Chisallo kernel or the Fourier kernel, the Chisallo means of the summation of Fourier series. It's a very good series. It converges to f as long as, well, at point f is continuous. And this convergent, if f is continuous everywhere, it's uniform convergent. Okay? Any question? Any question? And then we have a sort of very nice corollary for this. The first one is, if f is integrable and f hat of n equals to 0 for any n, okay, then fx equals to 0 whenever f is continuous at x. The uniqueness of Fourier coefficients. Why this is true? Why this is true? From the Fourier theorem, why this is a corollary to that? Why is that? How can you see this from our Fourier kernel is a good kernel? It's a family of good kernel. How can we see that? Any idea? Any idea? Okay, so you can see that if all the Fourier coefficient of f is 0, and at this continuous point of f, it can be approximated by this Fourier, well, the Chisallo means of this Fourier coefficient of the Fourier series, right? But whatever it is, it's just some kind of partial sum of the Fourier sequence, right? Of the Fourier series. But if all the Fourier sequence, all the Fourier coefficients are 0, so everything is just 0, right? So sigma n of f equals to 0 identically. And we know that whenever f is continuous at a point, the sigma n will tend to f, right? F convolved with fn evaluated at x will tend to f whenever f is continuous at x. But that convolution is just 0. You don't have anything else. So your f must equals to 0 whenever f is continuous at x. Okay? Any question? Okay. Another corollary is, well, the continuous function where continuous functions on the circle can be approximately uniformly approximate by trigonometry polynomial. Okay, why is that? Well, simply because, again, if f is continuous, then this kind of thing can approximate this f uniformly, right? What is this kind of thing? It's just some average of your Fourier coefficient, Fourier sequence, right? It's the average of your Fourier series, but each one of them are just a partial sum of Fourier series. So which means each one of them is just a trigonometry polynomial. And you take an average, of course, it's still a trigonometry polynomial. So this kind of thing can approximate any continuous function. Okay? So this two application of the Fourier's kernel and Fourier's theorems. And it seems that today we don't have enough time to tell you what is the Abel sum. And by using the Abel summation of Fourier coefficient of the Fourier series, we are able to solve the Laplace equation on the unit disk. Everything will be solved. So we are going to talk about it next week on Tuesday. Okay? So that's the end of today, and I hope you have a good weekend. And let me end the recording. And I will be here